So, this is your belated Chapter 4 video for the physics of the universe. And, a lot of this is going to correspond to playground physics. We're the stuff we're going over in a physics class. A lot of you can probably skip this or just look at the highlights and see it when you actually do the physics. And we've done a fair amount of it already. But, obviously some of you that's not taking physics should see this. So we're going to go through it. And, the big topics here is how do things move? What does energy look like? Or how do we understand energy? And how does gravity look? And we get to talk about Isaac Newton a bunch. So, we describe motion a lot through speed and velocity and acceleration. Right? We're describing how fast things are moving and how fast that changes. So speed is just distance over time. It's what you typically think of. It doesn't have a direction associated with it. You can go 100 miles an hour, and it doesn't matter which direction you go in. You're still going 100 miles an hour. But velocity and acceleration are vectors. They have a direction associated with them. And there's a reason for that. Is it matters if you're trying to go somewhere that you go in the correct direction. Right? So velocity is speed with a direction, 10 meters a second due east. And acceleration is the rate at which that changes. Right? So on Earth, things fall due to gravity, and that gravity acceleration is about 10 meters per second squared. So if you drop something off a building, 1 second later it's going 10 meters per second. The next second, so 2 seconds later, it's increased by 10 meters a second. So now it's going 20 meters a second. And it'll continue to do that until it hits the ground. Gravity is the same for everything. The way Galileo showed it is by rolling objects down a ramp. He did not do the thing that you have probably heard of dropping cannonballs off the Leaning Tower of Pisa, if you've heard of that. Some people don't hear of it anymore, but he didn't do that, if you have heard of it. He did a very simpler experiment. However, we did do something to confirm it, right, is most falling objects on Earth experience the air, and so there's air resistance. And so I invite y'all to go look at this where we remove the air in a very convoluted manner by going to the moon. But we drop a hammer and a feather at the same time, and they hit the ground at the same time. And the astronaut is suitably impressed. So when we talk about velocity and acceleration, we should also talk about the mass. If we want to talk about how objects can interact, it becomes important to talk about the mass. You can imagine a bug flying through the air and it gets hit by the windshield of a car. The bug certainly would, if it hit someone in the face, it would hurt. But the truck weighs so much more, it just obliterates the bug. And so it's not just how fast something's going, which these speeds you can measure relatively to each other. The truck's going 60 miles an hour, then to the truck's perspective, so is the bug when it hits. So what matters is mass times the velocity, which is what we call the momentum. If there's a change in the momentum, that means there's a change in the acceleration, and change in the velocity and an acceleration. The change in the momentum is what we call a force or a net force. Forces are pushing and pulling things between objects. But the net force is the thing that causes a change in momentum, which generally means a change in acceleration. It could change the mass, but it usually changes the velocity, and so you get an acceleration. When things rotate, you also get angular momentum, and we'll define that a bit later. And so sometimes we want to distinguish between mass and weight. I'll often talk about weighing an object, and that's not what I mean. I mean finding the mass of the object. The mass is just the amount of matter. We just count particles, essentially. But the weight is a force, a gravitational force that acts on it. Right? And importantly, when we try to measure it, we're often not measuring the weight either. If we set a scale up and stand on it, we're not measuring the weight, we're measuring how much a set of springs are compressed. What is the support force that the scale can provide? And you can put yourself in situations where that can be larger or smaller. If you skydive and jump out with a scale and put it under your feet, you don't weigh anything because the scale can't provide a support force. Right? If you're in free fall, you're weightless. Gravity is still acting on you, which we'll talk about in the future, but you don't feel it. When you feel weight, you feel support forces holding you up. And that's what's happening. There is gravity in space. I asked y'all in the homework to calculate the weight of someone in orbit, and you find it's about 85% of their weight on Earth. There's gravity in space, but weightlessness is because you're free falling. You can imagine jumping off of this platform. The example Isaac Newton came up with was shooting a cannon off of a tall mountain. It's the same. With a little bit of speed, you land near the platform. With a little bit more speed, you land further away. With the correct speed, you follow the curvature of the earth and you never land. Is that every time you fall down, you've moved so far over, you've not lost any height. So weightlessness in orbit is due to having constant free fall. I got to talk about Newton. Newton was kind of a grumpy old man and sort of a polymath, the way we'd put it. He did a lot of different stuff. He studied light, and he studied it in a very peculiar way by looking at how the eye handled light when it deformed by poking himself in the eye. He studied alchemy, and so he kind of had a lot of mercury and went a little loopy at the end. He built calculus, he built telescopes, and he built the necessary understanding of gravity that we need. And so effectively, he came about with the principle that physics works uniformly everywhere in the universe, which is kind of important. There's no special place. The Earth is not special. And he came up with laws of motion, and he's codifying the ideas that Galileo is putting forth and getting rid of all the bad ones that Aristotle had. So we'll just state what they are. The first law is not really special. Don't worry too much about it. Objects keep their velocity. They keep a constant velocity unless a force changes them. That's a special case of the second law, which is if there's a force, you have a change in velocity. And really what he said was if you have a force, you have a change in momentum. You could change the mass, but usually you change the velocity. And that means force is mass times acceleration. And then he had a third law, which is talking about the interactions between objects. And the third law says that if one object pushes on another, then that second object reacts and pushes on the first. And they're the same size force, and they're in opposite directions. And so you've heard for every force, there's an equal and opposite reaction force. He never said that. He said something more along the lines of the first thing I said is there's when things interact, they apply equal forces to each other in opposite directions. So I also asked y'all in the notes, I gave y'all some articles and stuff about different people and what they did and different topics. In particular, a big part of this is conservation laws. And so we want to talk about why certain things don't change. That's what we mean by conservation laws is we find something that doesn't change. And we'll talk about what that means. But I asked y'all to look up Emmy Nether. I know it doesn't look like I pronounced it right, but I did, I think. Who got this idea of associating conservation laws with symmetry in a situation. So we'll talk about that a bit. So you want to read those articles a bit. Anyway, conservation laws. Newton's third law has to do with the interaction between objects. So we look at the interaction, in this case a collision, and we look at the momentum that the objects have. And no matter how we do the collision, if we can account for all the forces that are external to these objects and get rid of them, so effectively just looking at the objects interacting, the momentum doesn't change, the total. Now it moves between them, and Newton's third law tells you how it moves between them. It's the forces that each object applies on the other, those third law forces. But in the whole thing, the system, the green picture here, what we have is both objects have a total of mass times velocity before and after. Now, if these masses are different, then the velocities change. But the product, the momentum, doesn't. So there's a symmetry here. And the symmetry that comes up is that it doesn't matter where you are in space, physics holds. That seems like an odd one, but that's where it comes from, is it doesn't matter if you see velocity in front of you or 10,000 light years away, the physics that's going on cause something to move should be the same. All right. So there's also angular momentum, and I thought I'd talk about that. I want to bring it up in terms of an object orbiting the sun, a planet, let's say. And we've already talked about this. Kepler's second law says that, Kepler's second law says equal areas and equal times. And what that is, well, it's saying that if you're far away from the sun, you get a long, skinny triangle for your area. That means your velocity is slow. If you're close to the sun, you get a short, fat triangle, which means your velocity is big. And both of those are really a statement of conservation of angular momentum. So we have to define angular momentum. The momentum is mass times velocity. The angular momentum is mass times velocity times distance that you're rotating around an object. And so what we find is if there's not an external force, what we call a torque, it causes a twisting. There's no external forces. This product of mass times velocity times radius should stay the same for everything that's orbiting. What I mean by that is, if I go back a slide, you can calculate an angular momentum for this planet going on this orbit, but you can also calculate one or the sun. You can pretend that the planet's stationary. You can say the Earth is stationary and the sun orbits. And while that's not apparently true, you can pretend that it is and calculate a angular momentum for the sun orbiting. And the sun may actually be moving, right? We talked about that in chapter 1. The sun has speed as it moves around the galaxy. So it may be moving relative to the planet and has angular momentum, and that's also conserved. And also these objects can be spinning, and that's also angular momentum. So you have to add up all the different sources of angular momentum. But if you do, that's a constant. There's no, without a twisting force, without a torque, the orbits continue on and on. They basically change these variables of mass times velocity, but they don't change the total, the angular momentum. And this is a symmetry that's involved with rotations. It doesn't matter if you look to your left or your right, physics should look the same. And so you've seen angular momentum if you've seen figure skating or any sort of, if you're in the physics class, you will see me do this sort of experiment of changing my mass distribution. An idea is that more mass is out in your arms. When you pull your arms in, you decrease the radius. That means you increase the velocity. All right, so energy. We know energy when we see it. Energy is either the motion of matter or the potential for matter to be moved. So you can think of it as there's energy in dropping an object, dropping a hammer on the moon, but there's also energy in holding that hammer up. It's available for you to use in some way. And we can account for it. And effectively, what we're finding is as long as we account for it all, then we can transfer it between objects. We can change the form of the energy, but it's always conserved. And this comes from a symmetry that's unusual, is that the laws of physics are consistent now and in the future, or running time backwards. Right? Is that things should make sense if we wait 1,000 years and then observe something, or it should make sense if we start with, let's say we videotape a motion. If we play it backwards, the math still works out. I mean, it doesn't always make sense. If I throw an egg at a building and the egg cracks and then I've done a vandalism, then you can't reassemble the egg and throw it back the other way. There is a direction for time. But the object moving in the air looks the same forwards and backwards. So there's types of energy. There's the energy associated with motion, what's called kinetic energy. There's energy that's stored, that's available to be used. Potential energy. One form is in gravity, taking something far away from a heavy object and then letting it go. Another form is chemical potential energy. There's some others. And then there's light as energy in transport. It goes from one place to another. So you can change the type, but you can't create it and you can't destroy it. Right. So I asked y'all a question in the homework about sticking your hand in an oven versus sticking it in a pot of water. It's boiling. And so objects can have energy that's associated with how fast the individual particles are moving. And if the average particle is moving very fast, it probably has a lot of kinetic energy in the particles in the material. And so we define temperature as a way of talking about the average kinetic energy of a particular particle in the system. We average over all of them. And so in the picture here, stuff that's moving at low speeds has low temperature. Stuff that's moving at high speeds have high temperature. So we can look at these. These look like the same materials, so we can say the higher temperature thing has a higher thermal energy. But it matters what the thing is. When we talk about sticking your hand in an oven where there's hot air, there's fewer particles of air, and it's harder for the energy to transfer to you. You stick your hand in boiling water, there's lots of particles of water, and even though each one has less energy, there's a larger total. So thermal energy has to do with the total energy that an object has. The temperature is talking about the average energy per particle. So that's kind of important. I'm assuming y'all know about, you've taken science classes, you know about temperature scales. Celsius was used, dividing 100 measurements between freezing and boiling points of water. Kelvin is making sure there's no negative temperatures. And it comes from, if you heat something up, it stretches. If you heat a gas up, it expands. If you cool it down, it contracts. How much do you have to cool it down until it contracts no further, until the particles have no kinetic energy? So 0 Kelvin is 0 kinetic energy, effectively. And in Fahrenheit's the weird one, but everyone knows it. And it comes from, when you build thermometers, you want to have nice, easy ways of dividing. Dividing by 2 is easy. And so we wanted 64 divisions between the freezing point of water and the average body temperature. And that correlates to 180 divisions between freezing water and boiling water. But that is, you build a thermometer and then you can measure someone's temperature with it, or you can measure water temperature. So the normal experience that people have with temperature, wandering around their day, you want something that can measure those temperatures, and it's very easy to divide by 64. So that's where that comes from. That's why everything's so weird with Fahrenheit. Anyway, temperature scales talk about the, effectively, when we talk about temperature in Kelvin, we're talking about measuring the kinetic energy of, the average particle. But total energy has to do with how many particles are, the density of the material, and the temperature. Okay, did I get sidetracked? I had to answer an email. That was weird, so that's okay. Anyway, we're talking about thermal energy and the density of stuff and temperature. All right, so there's also gravitational potential energy. If you throw an object upwards, it slows down, but the energy doesn't change. It has to go somewhere. And what it is it's stored in the height of the object. You turn the kinetic energy of the thing moving upwards. As it slows down, that kinetic energy turns into potential energy, and then it comes back when the object falls. So you can store energy by lifting an object up and then release it by dropping it. In the universe, what that's going to mean is if you have a bunch of mass that's spread out, it has a lot of gravitational potential energy. It could collapse and speed up a bunch of particles that's in the, here we have a gas cloud, let's say. This could be a light year across, and we collapse it down very quickly. We're going to make some particles that were moving very, very, very slowly, very far away, move very fast as it falls inwards. It converts gravitational energy to first kinetic energy, and then it's kinetic energy of a bunch of stuff moving around. That's thermal energy. So in the universe, gravitational energy gets turned into heat. Matter itself is a form of potential energy. You can release energy by converting matter to energy. Basically, you do it through nuclear reactions. We'll talk about those more probably second semester when we talk about stars. But effectively, you know, a small amount of mass is a huge store of potential energy. And we can also go backwards. We can generally it's shooting very high energy light and getting it in a point where it's concentrated and it will create particles. So the total energy of the universe is fixed. When we say energy is conserved, it means that if we account for all of it, then we find that it's the same before and after something happens. We can change the form, but we have to keep track that we understand what form the energy is in. All right, so a lot of that is talking about motion, and we still aren't done with Isaac Newton. He also figured out gravity and figured out a way of explaining it, and claimed and proved that it's universal. It's like gravity acts throughout the universe. So if you have massive objects, every mass attracts every other mass. That attraction, the strength of the attraction, the force that you feel, is directly proportional to the masses. If I increase one of these masses, if I double it, I double the force. And it's inversely proportional to the square of the distance. So if I spread this out, if I double the distance between them, the force goes down down to a quarter of its size. So if we want to calculate that force, we have this formula. G here is a constant, which you can look up at 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And those units are to fix these, because we talk about units, kilograms and meters and seconds, but we could define units such that all we need is the product of the masses and the distance squared. So we could make G 1, but we actually want real units we deal with, so G has units. It's a weird number. So Newton took this idea of gravity to explain the orbits. So Kepler talked how orbits work, but not why. And Newton explained the why of it is that objects feel gravitational forces, and you can have different types of orbits. So the planets orbit in these elliptical orbits, which are bound. So what Newton said was all orbits are conic sections. If you studied conic sections in your math classes, ellipses and circles are one set, but there's also parabolas and hyperbolas. And what determines whether an orbit is bound or unbound is how much energy is available. Is it if there's a limited amount of energy, you have a bound orbit. But if something can come in with a lot of energy and it can go away with a lot of energy, and you have, but effectively an orbit is a trading between kinetic and potential energy. And so the type of orbit says what you start out with, effectively. So objects, when they orbit, they don't orbit the way you think. A planet orbits a star. Objects orbit each other. Now, when we talk about how they orbit, we want to talk about the center of mass. And for equal mass things, you can see, obviously, that one object will orbit another. When we talk about Pluto, Pluto has a moon that's almost as big as Pluto. It's a significant fraction. So, it'll look like this middle picture. Let's put on a pointer. All right, is Pluto will orbit a common point with its moon. But when we talk about a star and a planet, though the star is so much more massive that the point that the star orbits is inside of the star. So it looks like the planet moves and the star doesn't. But both objects orbit a common center of mass. So Newton is effectively going to extend Kepler's third law to allow us to explain all possible orbits, not just orbits of planets around the sun. Right? The reason Kepler's law looked the way it did is they didn't have good measurements of what a year is or what an astronomical unit is. But they knew that they could compare, and they could say, well, Venus's orbit is 6/10 or 7/10 of Earth's orbital distance, or Mars's is 1.6 Earth's. So they could find ratios between the planets. And so they set the units, and that's why it has this nice formula that you've seen, p squared is a cubed. But Newton applies it everywhere, and everywhere we're doing everything in kilograms, meters, and seconds. And so you get this form of it. It still has that p squared is a cubed, but this thing includes the masses. Larger masses will result in a change in the period or the distance. And it has this unit setting thing, g over 4 pi squared. So in general, when we talk about things orbiting, we're usually talking about a small object orbiting a large one. A moon around a planet, or a planet around the sun, or a star, or a satellite around the Earth. And we can ignore one of the objects. Right? If we talk about a satellite going around the Earth, we're talking about 1,000 kilograms versus 10 to the 24 kilograms. The Earth wins. You can ignore everything else. So when we have equal-sized objects, then we look at the total mass. So orbits, we talked about orbits being a conservation of angular momentum, but they're also a conservation of energy. Right? We're not, all the things are conserved at once. It's not one and then the other. So when we talk about an object near the sun has high kinetic energy because it's going fast. And as it slows down, that energy has to go somewhere, and it's gravitational, and it's a potential energy. And so the total energy, the gravitational plus the kinetic, is a constant. And that means orbits don't change. They're steady. Now, if they do change, that means there's an outside force, and we'll talk about that. If you want to change an orbit, right, let's say we send an object like a comet towards a planet. It might be on one type of orbit, but the outside force, the planet, is there to bend, to be a gravitational encounter and put it on a new orbit. There's some other things too, like when we orbit satellites, we think that there's no air, but the atmosphere goes up considerable. And even if there's a very tenuous amount of air, there's still particles there. And so there's friction and atmospheric drag. It can happen. But usually, when we talk about sending spacecraft somewhere, or when we talk about orbits amongst objects changing, it's gravitational encounters. Okay. Or it could be rocket motors. We could attach a rocket motor to the thing and try to launch it somewhere. And so we can ask, well, how much energy do we need to actually break an orbit to make it unbound? And an unbound orbit means that the object can go as far away as it wants, effectively to infinity. And so we call that escape velocity. And we can calculate what that is. For Earth, it's about 11 kilometers a second. But there's a formula for it. And if you read in your text, there's a formula for the orbital speed. Something orbiting the Earth is going to go about 7 kilometers a second. And it turns out you basically have to double that to get away. Right? So your escape velocity looks like 2gm over r, take the square root of that. So I would recommend looking in your textbook for that. Basically, for all the things that I'm asking you to calculate for, there is an example in your textbook that you can find how to work with that formula. So one more thing that gravity does, and I'm not sure if Newton talked about it very much, but certainly it's come up a lot, and it would have absolutely been known in Newton's time, but the explanation might not have. We notice tides on Earth. And it's a cyclical thing, and it has a cycle over a day and over a month. And we could absolutely believe that it has something to do with the moon and with the rotation of the Earth. The idea is that when we talk about the force of gravity, we pretend that an object is at one point. All the mass is at one point, but that's not true. We have the Earth. The Earth's a big thing. Its diameter is like 12,000 kilometers, and there's water on top of it, which is very free to move. So the idea is one part of the Earth is a little bit closer to the moon than the other, and it has a little bit larger of a gravitational force, which means it stretches. The Earth stretches out, and it's not just the water. The land stretches out, but the water is so free to move. That's the thing that we notice. That basically the near side of the Earth to the moon has water being pulled away from the Earth, and then the far side of the Earth is being pulled away from the water. And so we see these bulges form. These are our tides. Now, the appearance of tides in a particular like harbor or lake is going to be different because it's going to be dependent upon the geology, the geography of the land. But in general, there's always these two tidal bulges. And the size of the tides depend on the orientation of the moon and the sun, because the sun also has it. Now, the sun is much, much more massive, but it's much, much more far away, and its tidal forces are less, but comparable. And so sometimes you get the sun and the moon in line and you get extra big tides. Sometimes they're at right angles and they're fighting each other. Effectively, you have sort of a more uniform body of water. So the water is rotating with the Earth, and so what happens is the water bulge rotates ahead of the moon. And so there's a slight force backwards on it. Effectively, what we get is a friction between the water and the Earth's rotation. And this tidal friction slows down the Earth's rotation. Now, what that means is it changes its angular momentum. That has to go somewhere, and the thing that's causing it is the moon. So the moon gains angular momentum, which means it has to change its orbit slightly. It has to get farther away in order to speed up appropriately to change it. And so the moon used to orbit a lot faster, but tidal friction has caused it to lock. And so it orbits with one face facing us, basically because the moon felt tides as well. And it caused it to lose angular momentum until it was synchronous with the Earth. So it orbits at the same rate as it rotates. Okay. So we talked about objects falling, and all objects fall at the same rate. We can actually calculate the forces on different objects. And effectively what happens is the mass of the object cancels out. The thing that governs the acceleration of an object is the Earth's mass. That seems an unusual thing because when we talk about mass, we kind of talk about different sorts of mass. We talk about Newton's second law here that's written on the left is talking about the inertial mass of an object. How hard is it to accelerate? But there's also the gravitational mass, which is written on the right. And those masses are equal, but there's no reason for them to be, and we didn't understand why they might be. We'll talk more about that when we talk about relativity in winter. All right, so that is chapter 4. Next is chapter 5, and we conclude the video there.